Great. Okay. All right, let's get started. Hi, everyone. Thanks for coming along to this meeting of the Formal Demography Working Group. Um, this week, before we get started, I just wanted to also announce that Vanessa and I have are very excited to welcome a new co-organizer, Antonino Polizzi, who is a research scientist at the Max Planck Institute of Demographic Research, does a lot of formal demography work in both fertility and mortality. He's coming on as a co-organizer, so we're very happy. And so welcome, Antonino.
Welcome.
Um,
Thank you.
okay, so this week we've got Chiara Micheletti t speaking with us today. So Chiara is a PhD student in demography at SED at the Autonomous University of Barcelona and also at the Max Planck Institute for Demographic Research. Her research focuses on mathematical demography with an emphasis on mortality and health. So, for example, she has a publication in demographic research that was part of the special collection in memory of Jim Pell, looking at the relationship between life expectancy, modal age at death, and threshold age of life table entropy. So today, Chiara is going to be talking to us about cardiovascular incidence and survival inequalities in Finland. Thank you so much for joining us today. Really excited for your talk.
Thank you for having me and inviting me. And thanks for the introduction. Yeah, I'm not really going to talk to you about a lot about CVD in Finland. It's an excuse and it's a flashy title. I'm gonna dive a bit deeper into the methodologies that we developed for this paper because I thought this is the right place where to do it and a place where I can finally have a formula on my slide without people figuring out. So this is joint work with my supervisors who are Alison Varralte and Iñaki Permañer, and the Finnish side, let's say, which are Pekka Martikainen and Shubh Sharma. And as Monica said, my research so far has been focusing on the good old question, is morbidity compressing or is it expanding? This is a question that has been in the literature for a very long time, and mostly because we've been observing general increase in life expectancy over the last century. And we tend to think that more is better, like more money is usually a better life, or more years to finish a PhD makes better mental health status. But that's something else. So can we say the same of years of life? Because years of life can be spent in either good or less than good health. And so people were asking themselves, how are we living these years that we are adding to our lives? In the literature, we can identify three main theories, three different hypotheses. There is a more one that it's seen as a more optimistic one, which is the compression of morbidity hypothesis, that states that these gains that we have been observing in longevity are being achieved through by gradually pushing the onset of morbidity towards the last years of life. On the other side of the spectrum, we have the expansion of morbidity theory, which is seen a bit more as a pessimistic theory because it states that these extra years that we are living, we are gaining them by surviving. We are achieving them by the survival of people living longer in morbid states. And then in the middle, we have the dynamic equilibrium hypothesis that states that is in these extra years that we are adding to our lives, we will see a decrease in severe disability, but still an increase in mild and moderate disability. So usually to test which of this theory is ultimately unfolding, there are different strategies. A very common one is to calculate health indicators such as healthy life expectancy or unhealthy life expectancy. And these can be achieved in different methods. For example, a prevalence methods like the Sullivan method, or incidence methods like the multi-state methods. And once you calculate these indicators, you can check how they have changed between two time points. And you can do that in absolute terms. So if, for example, healthy life expectancy has been increasing in time, then you would argue that morbidity has compressed between the two time points. While if healthy life expectancy has decreased between the two time points, then you would say that we're spending less time healthy and therefore morbidity has expanded. We can also check these in relative terms, and a common way to do it is to calculate the healthy life expectancy over life expectancy ratio, which tells us which proportion of life we're spending healthy. And if this ratio increases, then once again, we would say that morbidity has been compressing between in time, while if the ratio decreases, we are spending a smaller share of our lives healthy, and therefore we're facing morbidity expansion. So this is a very common way to test morbidity dynamics, how it's evolving. They're evolving, and we want to propose an approach to add to this testing set. Let's say. So to do so, we put ourselves in what we call this bivariate framework that starts from the idea that we can take length of life and we can decompose it as a sum of years that are spent in good health and in less than good health. So if length of life is X, healthy years are H, and unhealthy years are U, we can write X as a simple sum of H and U. And this is very, very basic. It's one of the simplest equation you can come up with. And but this is where you see where this bivariate comes from, because we're not only interested in length of life that we've seen it's extending, but also in how it is composed in terms of health trajectories. And we move from just age to both healthy and unhealthy years. So we move from one dimension to two dimensions. And this idea that age might not be the only important time dimension to look at is quite present in the literature, is very common in epidemiology and survival analysis. Many times it's not enough to look at patients' age, but it might be important to look at, for example, time since disease onset or times since treatment. And this is also incorporated in very, very nicely in recent work by Angela Carollo and colleagues and other people, where they consider simultaneously multiple timescales to understand better phenomena where age is not enough. So, as I said, we put ourselves in this bivariate framework, and we take advantage of the work done by Tim Rife and colleagues that used this idea to construct a new multi-state life table through which we can generate these bivariate age-at-dash distributions that are able to incorporate information on the cumulated number of years each individual has spent in good health and in less than good health at time of death. So this is something a bit recent, so I thought a plot could maybe illustrate it better. When we deal with the classic age-at-death distribution, we usually have just a curve that for each age at death tells us how many people died at that age. So we have a unidimensional function, let's say. In this framework, we move from one dimension to two dimensions. So we just We don't want to look only at age at death, but we want to look at how this age at death was reached in terms of healthy and unhealthy years. So we move to a surface, and this is the new bivariate age at death distribution. In this case, people who die at the same age are aligned on the same diagonal. And depending on where they are on the diagonal, they will have accumulated less unhealthy years at time of death or more unhealthy years at time of death. So we move from a curve to a surface. In this case, if we take a point here, for example, we will have that this will give us the number of people that died at this age, which is the diagonal of age 90. But here in particular, they will have died with 80 years without any condition and 10 years with some kind of health impairment. So from this new bivariate distribution, we extract what we actually propose in this paper, which is the main topic of this talk, I would say, which is what we call the healthy years curves. And very plainly, these curves give us the average number of years lived healthy at each age of death. And we extract them by this bivariate distribution. You have here the formula. It's a simple conditional expected value. And here it's where you can see this dh of x minus h, which is the bivariate age distribution. So really the formula, it's again the description I gave before. We compute the average number of years lived in good health by those who died at age x. And we have this for each age, so when we plot it, we get a curve. Very nicely, for free, we get the unhealthy years curves, which is the opposite. We just changed the roles of healthy and unhealthy, so of H and U, if you remember the little letters. So in this case, the unhealthy years curves give you the average number of years lived unhealthy at each age of death. The formula is exactly the same. And a nice relationship that holds is that if we compute the curves, the healthy and unhealthy curves at a specific age, and we add them up, they give us back the age. Yeah. So we got into the bivariate framework. We saw the bivariate age at death distribution. We computed the curves, but now how do we actually use these healthy years curves to assess what is happening with morbidity? The short answer to this is we check how their relative position changes over time. And I will illustrate this with 3 scenarios. It's 3 cases that we can observe. We can consider 2 different time points, an earlier time point, T1, and a more recent time point, T2. And then let's say that this happens. So here in dark blue, you have the healthy year curve of the most recent period. And in orange, you have the healthy year curve of the earliest period. So the curve of the most recent period is below the curve of the earliest period for each age of death. So this means that people dying at whatever age in the most recent period, they were doing so by having accumulated on average a greater amount of years unhealthy. Or if you want, a smaller average number of years healthy. So in this case, we would say that morbidity has expanded. If the opposite happens, so if the most recent curve lays above the earliest curve for each age of death, then the average number of years spent healthy has increased for each age of death. And therefore, we are spending more time healthy, and we would say that morbidity has compressed between the 2 time points. But then we also have a scenario where the curves could cross, which is an interesting scenario. We can't probably say much on what's going on in general in terms of morbidity, expansion or compression, but we can see what's happening at each age at death. So for some ages at death, we can see that the average number of years spent healthy has decreased in time, and for others, that it has increased. So this is all the theoretical side of this talk. These are the curves, and I thought it was important also to show an application with real data and also to justify why I had Finland in my title. So I will present you here the results we got with the Finnish registers. We computed the curves for two different 5-year periods. The first one being from 2000 to 2004, and the other one from 2016 to 2020. We computed them for both men and women aged 40 plus. Since we had the data, because I guess many of you know that the registers are very rich, we computed them also for 3 different educational levels, distinguishing between basic, secondary, and tertiary education. And in this case, we focused on cardiovascular conditions. So for this application, being unhealthy means having been hospitalized for one of the CVD that you see listed on the slide. Since I guess for some people these curves are a bit new, I thought of putting a quick refreshment of how we read the curves just before diving into the curves for the data I presented. If you take a point on one of these curves, in this case, it will tell you that in this specific period, so in 2016, 2020, a Finnish female dying at age 70 had spent on average about 26 years without any CVD condition above age 40. So this is once again how we read the curves and what the curves can tell us point by point. And now we can jump into the curves for all the subpopulations that I listed before. So this is a bit maybe of a dense picture. I will walk you through it. First of all, we have men on the top, women on the bottom. We have the earliest period, 2000 to 2004 on the left, the most recent period, 2016 to 2020 on the right. You have a curve for each educational level, and the darkest the shade of the color, the higher the educational level. And finally, you have an annotation of the remaining life expectancy at age 40 for each subpopulation. So the first thing that we can look at is just these life expectancy levels and how they changed. They increased for all the subpopulations between the first and the second period. So we are seeing these longevity improvements. While one thing that is very clear from here is that the curves didn't change much. It's maybe not easy to see in this plot, and I will have other plots to see better what's going on. But there is not a dramatic change in what happens in the curves. And we can see when they don't overlap, even if there's a lot of overlapping, there is the educational gradient that we would expect. So the darker color is usually above the lighter color. And if we want to get a bit into the sex differences, but I will not spend time on this, we can see that the males curve, which are the one on top, depart earlier and further from the diagonal, which is consistent with the literature that usually finds that CVD onset happens earlier for men and they spend more time with the disease. I forgot to mention what it means, this diagonal. So if the curves were on the diagonal, it would mean that all the people dying at that age would have spent no years with a chronic condition. So they would have died healthy in terms of the CVDs we consider. but as I said at the beginning of the talk, the reason why we wanted to develop, we came up with these curves is to check if morbidity has expanded. So we need to check, or compressed. So we need to check how they change over time. It was not easy from the other plots, so we computed how the actual differences of the curves in 2016, 2020, and in 2000, 2004. So for each subpopulation, we took the most recent curve and we subtracted to it the earliest curve. And in this case, positive values here means that in 2016, 2020, the people dying at these ages had accumulated on average a greater amount of CVD-free years. So once again, the differences are small. You can see from the range, the values on the y-axis is not crazy things that are happening. Especially nothing is happening for tertiary educated men. So for them, no expansion, no compression of morbidity between these two periods. Maybe we can see a hint of compression for some population and some ages. In particular, it looks like men of the secondary and basic educational level dying between ages 60 and 80 had spent a bit more time CVD free dying in 2016, 2020 compared to those dying in the same ages in 2000, 2004. The same goes for women dying between around age 70 and 85 in 2016, 2020 compared to 2000 and 2004. While the situation is reversed for women dying at the earlier ages. So we see negative differences here, which means that women dying between age 40 and 70 in 2016, 2020 had done so by accumulating a bit more time with CVD compared to women dying at the same ages in 2000, 2004. You can see there is some crazy stuff going on at the older ages. It's not very nice. It's probably because small sample size, so I wouldn't trust too much or say much about what's going on here. Yeah, and then we can also see what happens with the ratio, which would be probably the standard way to do it so far. And the healthy life expectancy over life expectancy ratio basically didn't change over time, which is in line with the small differences that we found. There is a small decline only for tertiary educated women that go from 83% to 81% from the first to the second period. As I said, we developed the curve to understand morbidity dynamics, especially how it changes over time. But we can also we can use the curves to check how morbidity is experienced across other dimension. And one of these is the educational level that we have the advantage to have data for in these Finnish registers. And therefore we also checked how different the curves are across these levels. And in particular, here we computed the differences, the difference between the curve of the tertiary educated versus the basic educated, which is the one in the darker purple. And then the difference between the curve of the secondary educated versus the basic educated, which is the one in the lighter purple. And here positive differences indicate an advantage for the higher educated. And we can see that, as expected, the greatest advantage is for the tertiary educated. We can see that somewhere for some ages of death, the differences declined between one period to the next. But we can also see that for some ages of death, the differences increased from one period to the next, as is the case, for example, for women dying between age 70 and 90. The differences increase from tertiary to basic. So, quick summary of the results. The curves did not change dramatically between the two periods. The longevity gains that we are observed, that we can infer from this increase in life expectancy that we saw, are not actually accompanied by a significant change in the duration of life spent with CVDs. So are we going, is there some kind of stagnation in the time spent with the disease that is happening? The educational gradient in inequalities is confirmed. So tertiary educated individuals demonstrate advantages over those with lower educated education in terms of the average number of time spent CVD free at death. And a general consideration on the curves is that they can be used to assess morbidity evolution over time as we intended, but we can also use them to check how the morbidity burden varies across different dimensions. For example, at the educational level that we saw, but we can check sex differences, or if we want to stay in the inequality framing, if you want to think about inequalities, we can use other indications of socioeconomic status. Since I usually go too fast, I had an extra application. Is it fine if I show it?
Yep.
Okay.
Sounds good.
So I wanted to show this application because I think the curves here are a bit more interesting. Nothing against Finland, but in this case we have Danish registers and we compute the curves for 2 single years, 2008 and 2018, for men and women aged 50 plus. And here we look at chronic conditions. So in this case, being unhealthy means having at least one chronic condition from a specific list that we drafted. So here are the curves for in this Danish case. I think it's more interesting because it's the cross and it's the third scenario it's the third of the scenarios that I presented earlier. In this case, we have females on the left, males on the right. The orange curve is 2008 and the blue curve is 2018. As we saw before, when this happens, maybe we cannot claim anything specific on what's going on in general, like morbidity is clearly expanding or compressing or so on. But we can say that between 2008 and 2018, we can see some kind of compression for the ages between 65 and 80. And this is because the 2018 curve is above the 2008 curve in this age range, which means that, and this happens more or less for both sexes, and this means that individuals dying in these ages in 2018 had done so by accumulating more healthy years in terms of chronic conditions compared to people dying at the same ages in 2008. And the opposite happens at the older ages. So we would say that here we are seeing some kind of expansion of chronic morbidity because people dying at these ages in 2018 had accumulated on average less healthy years than people dying at the same ages in 2008. If in this case we were to look at the ratio, for women we would say that nothing is happening. which is not really what the curves show. While for the men, we would say that instead there is a slight expansion of chronic morbidity between 2008 and 2018. So I wanted to show this because if we were just to look at the ratio, maybe we wouldn't see many other things that are going on. And so we believe that the curves can give a bit of a more nuanced picture than just by looking at the ratio. Because we were able to see that something is changing, and we are able to see at which ages this morbidity change is happening. And but for sure, the ratio is much easier to compute and it's very much less data demanding. So we are not, and once again, I want to stress that we propose this not to substitute, but to complement this analysis. And I guess you came up with a lot of, or some kind of motivations, but I think one of the biggest ones here is that we compute no uncertainty for the curves. We didn't incorporate that. And as we saw in the Finnish case, the curves can be very similar. So can we actually say that the differences we see are significant? I don't know if we are protected by the fact that we use high quality registry data population level, but still, I think it would be nice to incorporate something like that. And maybe one day I will have the time to do that. So this is all from my side. Thank you very much.
Thank you very much, Chiara. Wonderful presentation. Really, really clear. Love the slides. Very cool, compression and expansion.
Yeah.
Questions from the audience? Feel free to raise your hand. One's being a bit shy. Maybe I'll ask one first then, just to get things started. So it seems like a really cool method, and I liked that you made it really clear like how it's sort of complementary to the sort of more traditional approaches. You used registry data in both examples, and I'm guessing, and you sort of said on the last slide that it is much more data intensive. So what data do you actually need to sort of calculate these curves? And can you get it from other sources that aren't registry data?
Yeah, we use registry data. I think I'm very lucky at the moment with this amount of information. But you need longitudinal data basically, because you need to track how long people lived and when they got sick, and then how long they stayed sick. Um, I think for now, for this application, I also it's an easier situation because we are considering conditions from which you cannot recover, or this is at least the assumption, and this is the way we select them. We assume that they have a huge impact or a big impact on your life, so they are actually chronic, and there is no reverse, like you cannot recover and move between the states if you think of a multi-state model. Um, so you need longitudinal data. You need to have the history of the people, and then you can understand. You can split the length of life in this sum of healthy and unhealthy years. You can compute transition probabilities from healthy to unhealthy, and so on. So it's not doable only with registry data, but you need panel data. I think, and yeah, Team Rife is the one, and other colleagues developed this bivariate distribution. It's based also on other work by other people. But I think the example they put out was with share data. So yeah, This is mainly the thing. The problem is not many time you have a high quality data in this form, I would say.
Yeah, no, I mean, yeah, I was thinking the share and the health and retirement study in the US and things you might be able
I
to.
think the first try Tim did was with HRS.
Yeah,
But I think then they went for the share. I don't know
yeah,
exactly what was the reason
yeah,
behind it, but you could use HRS as well.
yeah. Cool. When did you have a question and then you decided you didn't have a question, or do you still have
No,
One is
I
in
just
my office.
our office. You can see all the math in the back. It's pretty cool, actually. I was like, yeah. First day, I was just admiring it, and also, no, but I do have a question because like when you calculate these kind of like um, healthy life expectancies, a lot of the criticism are, oh, you have such a wide confidence intervals, and then like you can't make any kind of justifications about like any trend and stuff. Like how wide is the confidence interval here? Have you tried calculating them? I'm just like curious because
No, I haven't.
but I imagine with registered data you have much narrower like confidence intervals than HRS or like share. Um, but yeah, like especially did someone just give me a down or did I? No, that's all right. But the idea is like I guess like at age 100, like that downward trend, like just look at like kind of the confidence interval is probably going to be pretty wide. And then, yeah, I'm just curious. But thank you. It's a really good presentation. So congrats! Yay!
Thank you. No, we haven't. We haven't calculated confidence intervals on this, which is also why at the end I said that it's one of the limitations. Um, but yeah, the thing is, well, you could do some bootstrap maybe. Uh, but I haven't properly done anything on that yet. I maybe I hope we are protected enough with the data we have, but you don't always work with such data, so it's important to have um, to do that as well.
Thank you. Thank you.
Thanks, Wen, and I love the fact that you two are in the same room and you have the same color sweater on. Vanessa, did you have a question, and then Anna Christina, and then Hal?
Yeah, I was actually, yeah, just quick comments. So thanks again for accepting your invitation and coming. So I really think you mentioned this now at the end, that for me was a very important limitation to mention that you're using high quality data, which is of course the best to test a new method, but it's also because you're proposing as a complementary approach to using just averages or the ratio of averages. I think it would be important to really stress this, that if you don't have longitudinal data, you couldn't go towards that approach, right? And in that line, I was just curious with when you characterized your bivariate, so H plus U with less, you characterized it as, you defined it as less than good health. And I was just curious of how exactly you classify that in both scenarios. So for cardiovascular disease, you just said people that don't have any type of cardiovascular disease. So I was just a bit curious with more detailed of the data itself, because we know how sensitive these estimates are to how you categorize this. So for example, chronic disease as well, or chronic conditions, how did you how did you classify this, with less than one, more than two? And if you guys did some sensitivity analysis with this, like if you did different categories, what happened? If you saw any differences with different diseases, if it's something, if you compare the results in the literature with what you have and using only the ratios like you did in the end, if this is also similar for different conditions. I was really curious about that. But I also want to congratulate you, because I think we're in a very important moment in research agenda where everyone is just saying, look, we've had enough of the averages, in the sense that they're not telling us of course, we know they don't tell us the full story, but they're really, really limited. So any attempt to go beyond averages or the ratio of averages is really, really nice. So just curious. And one thing, just to use also Finnish data, including 2020, or was just the whole range? I just asked this because you would include deaths from COVID, and we know that cardiovascular disease was really increased at this moment in time. So I was also curious to see if some of the results you're getting there could somehow be driven by like an artificial increase in that year. Thanks.
Thank you. You might have to remind me some of the questions. So the data, yeah, strong limitations. I agree. I think now I am egoistically and selfishly thinking about my PhD. Like I want to do stuff and I need to try them out, and I have access to these and I take advantage of that. But I totally agree with you. The only thing I can do is see if it works. If it works, put it out, and then hope that at some point we will have data that covering all kind of like all countries, and we will be able to do this type of studies for them all. But for sure, it will be mentioned as a strong limitation in the paper, the fact that it requires very detailed data that are not usually available. So that was one of the questions. The other one was on the selection of the conditions. Yeah. Good question. Another question that I'm not, I don't know, I trusted people, let's say, in a way that we selected conditions that, as I said before, we were thinking they would impair life in a way that we could justify the fact that we were not allowing for recovery. So that was the how mostly we chose the conditions. For the cardiovascular conditions, we based our selection on another paper that they wrote for Finland that came out a couple of years ago. So we chose the same conditions, so we could also have a comparison and a sort of continuity in the study. But I've given presentations on these things a bit, and I always find people that are not happy with the selection we do. I think you will never satisfy all the people in the room with the selection of conditions that you decide to analyze, because some are too strong, some are like severity is too different. I don't know, and primary care or whatever. So I think that we are protecting ourselves also here, especially with the Finnish paper, by choosing a set of conditions that was already chosen in another paper, and also in this way we can compare results, which is another, I think, point you made. And so far we haven't. Once we have decided the pool of conditions, we've gone with it without checking other things. I think the thing we are trying to do now is being more neutral with the language we use, because in this presentation I thought it was fine because it's more on the formal side to use a generic language, so healthy and unhealthy, but we know that health is not a dual concept. So we will talk in the paper, we're talking more about condition free or with condition, CVD free or with CVD, talking about the CVD that we have selected in our list. So I think using a more neutral language is a better way to deal with it. Also because being healthy in this case doesn't actually mean being healthy. It means not having one of the conditions that we consider. So I don't know if this answers your question,
Of course.
but
Thanks.
yeah. And the last thing was having 2020 in the period of in the 5 year period of for Finland, I think. Yeah. I asked the same question when I got the data. I was like, why are we including 2020? But apparently, it wasn't affect changing the probabilities too much, and they decided to keep it. But this is how it was justified to me. I guess they did their their checks.
Okay, thanks. Thanks a lot.
Anna Christina?
Hi, Chiara. Thank you for the presentation. I have perhaps like a clarification question, and it's about when you compare the trends for different education groups. So you have your bivariate distribution, but if I understand correctly, there you're like averaging over one of your dimensions to be able to do the comparison, or not?
We extract the curves from the bivariate distribution,
Uh-huh.
and we compute the average number of years lived healthy, but by each people dying at a certain age. So we are moving across diagonals.
But you're flattening out one of your two dimensions because you have,
Well, we're not looking at marginals exactly,
okay.
but sort of. I don't know if for you the statistical notation helps, but it helped me. So we're looking at these expected values. So what is the expected value of age, the
Hmm.
healthy years, given that
Even.
you died at that age?
Okay, that was my question. Thank you.
Health death expectancy, actually.
Yeah, it's a bit of another perspective. Like you look at it not in the future, but from when you died.
Yeah.
Hal?
Hi, Chiara. Thank you. That was a really nice talk. There was a bunch of discussion a little while ago. People were talking about sources of data for this, and I wanted to mention one other one that did not come up. Especially in the medical literature, there's a very large literature on actual models for the transitions of individuals between different states of health, focused usually on a specific disease. One of the earliest ones of these was on cardiovascular disease by Franz Willekens and some of his students. There's examples for colorectal cancer that I've looked at. There's a ton of these kinds of things. They require longitudinal data, but they're not general. They're very specific to a condition. When you do that, you discover that the number of ways you can define healthiness is astronomical. Literally, the number of possible definitions of health in a relatively simple cancer model is much bigger than the estimated number of stars in the universe. So there is no such thing as a right definition of what you're going to call a healthy condition. It totally depends on what you're interested in. And if you have multiple versions of stages of a disease or severity of a disease, or some of these models also have the advantage that they include the care situation that the individual is in. Are you being cared for at home or in a care facility, in an institution of some kind? And so there's very rich possibilities there for different definitions of health that give you the same options of this. So it's a different approach than looking at an overall population like the total register data of a Scandinavian country. But I just wanted to mention that it is out there as as a branch of this field that this kind of analysis can be applied to as well.
Thank you, Hal. Yeah, this definition of health, will we ever find a solution? No. I think we have to acknowledge, and I think we have to be very clear about what we're talking, and the conclusions that we draw are very specific to what we consider. And for us, also, you mentioned severity. It's something we're not. I don't know if we have, but for sure we're not considering, and that also makes a difference. It's not the same if you spend 10 years with a condition and some kind of impairment and the same condition, but in a much that has affected you in a much worse way. So I think I don't think there is a solution, but the best way to tackle this is to be very, very, very clear and explicit on what you consider and the results that you have that are very specific to the definition you adopt and so on. But thanks
It's
for
basically a
sharing.
choice that you get to make.
Yeah. Yeah.
Thanks. Any other questions, comments?
I just think it's really cool, even though I know Tim already emphasized this in his paper, but I think you did it in a different way, that you're like this aspect of using different scales and that you're looking at death. I think this is really cool. And because it's different from, just doing just averaging and using the total life years lived that gives you this perspective. You're looking at like everyone that died already at that age. And then doing this by using DX function instead of using the total life years lived gives you a completely different perspective. And I think this is really, really cool. I mean, I don't know if it's too obvious for those who deal with life tables, but I think the way you guys are doing it is really, really different. And I think you should emphasize that. I think it's really, really cool. And that's why I joked. It's a little bit like when you said it's the average number of unhealthy years by those who die. So you really, the way you're like standardizing lives of unhealthiness by those who die and not by total life years lived. And this gives you a very different perspective. So it's like this sort of unhealthy death expectancy. And it's a little bit more accurate as well if you think about it, because then for the purpose you have, which is compression and expansion, because you're looking at those that did die and then going back and seeing how they live this life instead of just putting the whole thing together. I think this is really also cool, like to put it as an advantage of why doing this, why using this perspective. I think it's really, really cool.
Thank you. I really appreciate it because I'm in the last months of the PhD, so you can imagine it's a stressful moment. And to hear that someone likes it, it's nice. So thank you very much.
Yeah, no, seconded. It's great work, and you really explained everything really well. So, great presentation. Unless anyone else has some last words, I think we'll end there. Thanks so much to Chiara. Thanks so much for everyone for joining us. Stay tuned for the next meeting. And yeah, see you all again soon.
Thank you all. Bye.
And reach out to us if you want to present something.
Bye.